Welcome to the next lecture. Today we will study directional coupler. This is one of the important microwave hybrid circuit components. A directional coupler is basically a 4-port waveguide junction device, circuit, which can be symbolically represented as this. We have one primary port here and one secondary waveguide. This is primary waveguide and this is secondary waveguide, and this is port 2, port 4. Primary waveguide and secondary waveguide. One new terminology I will tell you, which is used in microwave circuits. So in classical circuits, you might have heard of when we are matching the load impedance. Okay. Similarly, in microwave devices, microwave circuits, we talk of characteristic impedance. Characteristic impedance is here equivalent of the usual load impedance while we try to match the circuits. You know that maximum power theorem and other things. Okay. And what will happen here in microwave junctions when we match all the ports with characteristic impedances? There will be no reflection, okay, and there will be a free transmission of power. What we say in usual circuits as maximum power transmission will occur. So when we will match each port with characteristic impedance, okay, then we will get free transmission of power. That is, there will be no loss, no reflection between port 1 and 2. Between port 1 and 3, and between port 2 and 3. Okay, between port 1 and 3, and between port 2 and 4. And there will be free transmission between port 1 and 2. Port 2. That is what it means. Between port 1 and port 2, there will be free transmission. And there will be no coupling. That is important. I will tell you what coupling means. There will be no coupling between port 1 and port 4. Coupling here you can think of, see, what you transmitted via primary waveguide here, that was intended for port 2 only. But if this directional coupler is designed in such a way that part of it gets coupled to port 4 also, that is what we mean by coupling. That wave is actually meant for port 2, but part of it gets passed through port 4 also. And there are two important characteristics of directional coupler by which we can get some quantitative idea of what is the coupling nature of the waveguide. There are two terms. One is called coupling factor, the other one is called directivity. Suppose a wave is propagated from, we have a source at port 1 and we want the EM wave to be transmitted to port 2 along the primary line. Then how will we define the coupling factor? In decibels, of course. It will be defined as 10 log to the base 10. Then you see, coupling means, I will again repeat, that you were intending to transmit the EM wave from port 1 to port 2, but because of design of directional coupler, there may be a leakage of power. A power will be coupled to port 4. So it is logical to define coupling factor as the ratio of power at port 1 and port 4. Now, second term is directivity. What does directivity mean? Directivity means that how well is the wave which is transmitted in the primary waveguide it is coupled to a specific port in secondary waveguide. Okay, so we want maximum transmission to occur from port 1 to port 2, right? We don't want that there should be any major reflection at port 3 especially. And now suppose we want a particular power to be coupled to port 4. So I will define directivity as the power at port 4 divided by the power reflected at port 3. As you can see, ideally you would like this reflected power to be 0, so ideal directivity should be infinity. But of course practically you can't have infinity directivity, but ideally we would like directivity to be as high as possible, in a way that the power at port 3 is as small as possible. This is the case when port 2 and port 4, as I told, are perfectly matched. They are matched with the characteristic impedance. You can think of analogously a normal circuit where we have a matched impedance, or even transmission line where we have matched impedance connected at the port 2 and port 4. Although practically you will see that directivity is high, not infinity. 30 to 35 dB are the practical values, but theoretically we would like to have this to be infinity. Now, how actually directional couplers are designed? There are several directional couplers. One is a two-hole directional coupler. The other is four-hole directional coupler. Similarly, there is a reverse coupling directional coupler, also called Schwinger directional coupler, SCHWINGER, Schwinger directional coupler. And then there is a something called Beth-Hole directional coupler. There are several directional couplers. We will right now concentrate only on a simple and which is commonly used two-hole directional coupler. This is how it looks like. You basically you can treat this as one waveguide, this one, and this as other waveguide, and here are those holes which are responsible for coupling as well as giving a directivity to this waveguide. We will now analyze it and try to see that how far away these two holes should be, such that we get desired properties of directional coupler. What are desired properties? Our directivity should be as high as possible, and accordingly the coupling factor should be have some reasonable value, but main thing is directivity should be as high as possible. Now let's see if we draw it like this. Okay, so here it is. I have chosen here the length L to be odd multiple of lambda g by 4. What is the reason for this? To understand it, we will first see what is the relationship between the phase change and the path difference. This is the path difference. You might have studied that in usual analysis of the waves. Suppose you have a phase change delta theta. Okay, this is the phase change, and let delta L be the path change or path difference. Okay, then you know that this delta theta over delta L, this will be equal to 2 pi divided by lambda. See, what is lambda? Lambda is the path. See, it is at 0 to 2 pi, and we also call it lambda. Lambda is the path difference corresponding to a phase change of 2 pi. So for any other arbitrary phase change, you can now find it is 2 pi by lambda times delta L, right? Now coming back to here delta L is your L, which is 2n plus 1 lambda g by 4. So the corresponding phase change between these two holes will be 2 pi by lambda g times 2n plus 1 lambda g by 4, which is 2n plus 1 pi by 2, right? So for n is equal to 0, 1, 2, so on and so forth. So it corresponds delta theta as pi by 2, 3 pi by 2, odd multiples of pi by 2. And what is its importance? You know that you are representing the electromagnetic wave in cosine or sine using sinusoidal or cosine function. And what will happen here? Now see, here is the incident wave. Part of it will get transmitted through this. Part of it will get transmitted along this path. Again, part of this will get transmitted through this, right? And here also, part of the wave will get transmitted along this port, and part of the wave will get transmitted along this port. Similarly, at this point, part of the wave will get transmitted along this port, and part of the wave will get transmitted along this port. Now, at this point, at this port, you are getting superposition of two waves with a path difference, which is odd multiple of lambda g by 4. In terms of phase, it is odd multiple of pi by 2. What happens to the superposition of two waves? Suppose if you take cos and or any exponential wave, so any cosine wave with a path difference of L, but there is one catch. Okay, there is one catch here. You see this mistake we usually make in analysis of waves. What is the definitely if you consider wave at this point and a wave at this point, this is a path difference of L, no doubt in this. But when a wave gets transmitted like this, look at it carefully, then at this, assuming this distance is very small, then the path difference is not L, it is 2L, right? L in this way and L in this way. Okay, so I should correct it here. Now this is for a single path. For overall phase difference, delta theta will be 2 pi by lambda g times 2L. This must be now clear. So which will be 2 pi by lambda g into 2 into 2n plus 1 lambda g by 4, which is 2n plus 1 pi. Yes. Now we have at this port 3, you have a superposition of two waves with phase difference pi. I'm sorry for previous mistake. So I only took initially this L, but L is only at this point and this point. When the wave gets transmitted via this path, then comes back here, it has covered 12 distance, 12 path difference, which is equivalent to pi or 3 pi or 5 pi depending upon the value of n phase difference. And this basic fact, if you have suppose cos of omega t as a wave and you add cos of omega t plus pi, it becomes 0. So at port 3, the overall sum of the waves gets cancelled, and here it will get added up because they will be in it's here in same phase. And now this way we have achieved what was our aim. You see the power at port 3 ideally will be now 0, and at port 4 we get a significant portion of the wave. Now with this, can we get some idea of how the S matrix of directional coupler looks like? S matrix. Unlike 3-port, if you recall, in 3-port it was not possible to match perfectly all the 3 ports. In other words, you could not avoid reflections in 3-port. Whereas in 4-port, we can have. You see here, we have wave incident at port 1. And we designed directional coupler in such a way that reflection at port 3 is 0. And there is no reflection at port 2 and port 4. Similarly, if you put the source at port 2, if you put the source at port 4 or port 3, the reflection at corresponding port will be 0, because this length L, it is a symmetric directional coupler. For this reason, we say that all 4 ports are completely matched. So the elements correspond to that is S11, which is equal to S22, which is equal to S33, S44. This will be 0. Whenever we have port matched, reflection components, which are diagonal components, will be 0. Also, you see there is no coupling between port 1 and port 3. So S13, which is same as S31 because of symmetry, is 0. In the same way, there will be no coupling between port 2 and port 4. If you now put a source at port 2, because of again the same path difference of 2 pi, path difference of L, there will be cancellation at port 4. Hence, symmetrically, S24 will be same as S42 will be 0. So our S matrix now becomes very simple. Here it is, every alternating term is 0. We have still lot of other properties of S matrix which we can use to further simplify the matrix. We will first of all use the 0 property. I will again recall 0 property so that it becomes, you understand it properly. In 0 property, you have the entry Sik. The second component you take their Sij conjugate, okay, and then you take the sum with respect to I. This will be equal to 0. If you apply it to here and taking into consideration that two terms are already 0, you will directly get these two relationships: S12 S14 conjugate plus S32 S34 conjugate is 0. Second one will be S21 S23 conjugate plus S41 S43 conjugate will be equal to 0. Similarly, we can use unity property. What is unity property? There you have Sij conjugate, you sum it over I, this becomes 1. So that we can write as S12 conjugate plus S14 conjugate equals 1. So now we will have to use these different equations to simplify. First of all, I will rewrite this as in this way. So if we take modulus on both the sides, we will get S12 mod of S12 mod S14 is same as mod S32 mod S34. Similarly, the second equation will give us directly, if you take modulus, these equations we get. Now using the symmetry property, that is S12 is S21, S14 is S41, S23 is S32, and S34 is S43. Now use them. What will you get? You will first of all see here, I will write it again. So it is mod of S12 mod of S14 is equal to, now instead of S21 I will write S12, and here I will write S23 is equal to, now instead of S41 I will write S14, and instead of S43 I will write S34, and even here I can write S23 instead of S32 because of symmetry, right? I can write S23. Now after I divide them, if you divide it here both the sides, so these two will get cancelled and these two will get cancelled, and what will you finally get is S23 here, sorry, S23 will be equal to S41 or S14, right? Because you will actually get S14 square is equal to S23 square, rather modulus. Okay. Similarly, if you take division other way around also, left hand side, right hand side, swap it, you will also get S12 modulus will be equal to S34. Okay. Now, to further simplify the things, let's take S12 S34, let that be equal to P. Okay. Then we will incorporate that one of the zero property, that is S21 S23 conjugate plus S41 S43 conjugate equal to 0. This we wrote above. Now after we incorporate it, we will write here, instead of S21 we will write P, then S23 conjugate plus, instead of S41, so we have assumed S12 is equal to S34, which is equal to P, right? So S34 is same as S43. Okay, so we will get here plus P times S41 equal to 0. One question may arise here. See, what is here P? P is a real. Okay. So one question may arise, why I have chosen S12 to be real? It can be anything. But we have a unity relationship. See here. S12 conjugate plus S14 conjugate is equal to 1. So it actually means S12 square plus mod of S14 square is equal to 1. One of them has to be real and one of them has to be imaginary. Okay, so you can see then only its sum will be 1. If you take both of them real, this is not possible, right? So this is the reason we will take one. We took S12 real. You will see S14 will automatically come to be imaginary. Now here is how. This we can also write as P into S23 conjugate plus S41 equals 0. Now see, this relationship, we assumed S12 to be real. This has to be imaginary, then only to be 1. Now if this is imaginary and we are adding a conjugate to an imaginary number, then they have to be conjugate of each other. So we can easily write that S41 will be of this form, J times Q, where Q is real and this is the iota. So S41 has to be pure imaginary. Now you see it satisfies this relationship easily, because S23 we also take as JQ. So S23 conjugate is minus JQ and their sum is 0, because P will not be equal to 0, that is a non-zero real number. And they satisfy the relationship P square plus Q square equal to 1. Okay, justification of let me add one point. Justification of S12 to be real and S14 to be imaginary is not only based on that this sum is 1. Yes, that can be positive. It is this sum is 1 as well as this relationship. Okay, that a conjugate of S23 plus S41 is 0. Summing, taking into consideration both these equalities, both these equations, we justify that S12 we can take as purely real and S14 we can take as purely imaginary. So now you can see that we can write S matrix now in a very simple way. So it is now in terms of only one actually unknown, because you have P square plus Q square is equal to 1, right? So we have only one unknown here. So this is one type of directional coupler which is very commonly used circuit in microwave junction devices. So in possibly this may be the last lecture of microwave components. I will see if we will sometimes, if I find some time in future lectures, we will touch the circulators and isolators. But mainly now, I will plan to start microwave, tubes, especially clustron, which is a very important microwave tube device. And we would try to do that one silicon device, one semiconductor device like gun diode, and possibly one recent microwave device also, which any amplifier which works at very high frequency. Okay, thank you.